Welcome to this walkthrough of the Global Hazard Intel project. We will begin by reviewing the project's documentation on its GitHub repository page. As we look at the main repository page, you can see the file structure and a brief About section on the right, which describes this as a multi-source environmental hazard intelligence system. Let's scroll down to read the full README document to understand what this project entails. Scrolling down, we arrive at the main Global Hazard Intel section. This platform is designed as a live environmental hazard intelligence tool. It fuses data from public weather services, air quality monitors, geocoding, satellite imagery, and NASA event feeds to detect various hazards such as dust storms, wildfire smoke, chemical leaks, and pollution spikes. The README notes that this is structured like a company-ready starter project. Continuing down the page, we see the core pipeline diagram. This text-based architecture chart outlines how satellite imagery, weather data, and air quality sensors feed into an AI hazard detection engine, which then outputs to a global hazard dashboard and API. Below that is a list of specific hazards covered and a representation of the repository layout. Moving further down, we find the quick start instructions. This is crucial for anyone wanting to run the project locally. The guide outlines 3 main steps. First, create a virtual environment. Second, install the necessary dependencies. And third, run the desktop monitoring app or start the API. The required terminal commands are conveniently provided in the code block below. As we scroll further, the documentation provides example endpoints for the API and lists the live data sources that power the system. These include various open Meteor APIs for geocoding, weather forecasts, and air quality, as well as NASA's EONet Events API and Esri World Imagery. Below this, the Desktop Analytics section explains the cross-functional design of the desktop application. Next, we see information about a research package included in the repository, outlining an IEEE-style LaTeX paper scaffold. This is followed by the product direction goals and the tech stack used to build the platform, which includes FastAPI, Pydantic, UVCon, PyTest, and a lightweight static dashboard prototype. Let's scroll back up to the top of the repository to quickly review the file list. You can see the main directories like .github/workflows, dashboard, docs, research, and the core source code folder src/global_hazard_intel. This structure matches the layout described in the README. To give you an idea of the depth of this project, let's briefly open the research paper mentioned earlier. This PDF, titled Global Hazard Intel, a multi-source environmental hazard intelligence system for atmospheric, health, and Earth observation analytics, provides a formal academic overview of the system's architecture and data flow, complete with an abstract and architectural diagram. Now that we have a solid understanding of the project from its documentation, let's set it up locally. We begin by opening the File Explorer to locate our project directory. Here, you can see the structured contents of our Python project, including folders like src for source code, tests, and configuration files such as .gitignore and docker compose. Next, we open this project in Visual Studio Code. The integrated terminal at the bottom shows that our Python virtual environment has been successfully activated. Looking at the editor, we currently have the desktop_app.py file open. Notice the code block responsible for building the application layout, utilizing TKI-Enkin's themed widgets to structure the pane window and configure the plotting areas. Moving to another file, we select reporting.py from the Explorer on the left. This file contains the logic for generating comprehensive reports. The cursor hovers near the _build_history_page function, which defines the figure size and layout for the historical data visualization within our reports. Now, let's launch the Global Hazard Intel application. The main dashboard appears, currently in an idle state. The interface is divided into a mission control panel at the top for query configuration, 4 empty plotting areas on the left, and an analysis briefing text panel on the right. To begin monitoring, we interact with the mission control panel. We change the query type drop-down to address. We then enter Berlin into the text query field and set the refresh seconds to 10. Click the Start Live Detection button. A status message appears below the input fields indicating starting live detection for Berlin. Within a few moments, the application fetches the data and updates the dashboard. The state changes to live and the region is resolved to Berlin, Deutschland. The plotting areas are now populated. A temporal detection trend graph, a satellite reconnaissance view showing a map of the Berlin area, and a signal intensity panel displaying horizontal bar charts for various metrics like SO2, wind, and PM 2.5. Over on the right, the analysis briefing panel displays an executive and partner value summary. Let's explore the briefing details further. Click on the Overview tab within the Analysis Briefing section. This view provides a detailed textual breakdown of the current console state, the resolved location coordinates, and specific readings for hazards, weather conditions like temperature and wind speed, and air quality metrics. After monitoring the live feed, we initiate the report generation process. Once complete, we switch back to the File Explorer and navigate into the Reports folder, then open the newly created time-stamped folder for Berlin_Deutschland. This folder contains several exported files, including Excel spreadsheets and a JSON summary. Double-click the hazard_report PDF file to review it. The PDF opens in the Chrome browser. This integrated stakeholder hazard report provides a clean, printable format of our findings. Scrolling down the first page, we see the query details, the enterprise priority score, and an executive summary outlining the value of this multi-stakeholder data fusion. Scrolling further down to page 5 of the report, we review the scientific and explainability notes. This section is crucial for transparency, detailing the data provenance from sources like OpenMeteor and NASA EONet. It also provides specific trigger explanations, quantifying how different variables like USAQI and wind gusts contributed to the overall signal, along with their respective confidence levels. Finally, we close the browser and return to the File Explorer, concluding our review of the automated hazard intelligence workflow.